Nuclear fission takes place when an atom's nucleus splits into two or more smaller nuclei. These smaller nuclei are called fission products. Particles, example neutrons, photons, alpha particles, usually are released too. This is an exothermic process, releasing kinetic energy of the fission products and energy in the form of gamma radiation. It also releases heat. This heat is used to boil water, which turns electrical generators. Radioactive decay proceeds according to the principle called the half-life. The half-life is the least amount of time necessary for one half of the radioactive isotopes to decay into another element. For example, the isotope measured on the graph starts at 100% of a particular isotope. After 1 year, the amount of original isotope is reduced by half. Another 2 years is required for the remaining isotope to be reduced by another half, at which point the current amount of the original isotope has been reduced to 25%. Notice that each successive half-life requires double the amount of time as the preceding half-life. This is because there is 1/2 less the original amount of isotope at the beginning of each successive half-life period. Half-life reactions are nuclear reactions, that is, reactions that take place within the nucleus. They are also called radioactive decay or radioactivity reactions. They are spontaneous, that is, that they are not caused by any outside force or energy. Reaction rates remain constant, not affected by temperature, pressure, or addition of a catalyst. Radioisotopes are atoms with unstable nuclei. The unstable nucleus has a disproportional ratio of protons to neutrons. That is, a disproportional ratio to the most common isotope. This disproportional ratio causes the unstable nucleus to decay spontaneously. When the decay happens, it leads to a change in the number of protons. It transforms that atom to an atom of a different element. In this example, we see the parent isotope, radium-88, undergo alpha decay, that is 2 neutrons and 2 protons, to the daughter isotope, radon-86. This reaction is spontaneous because it results in a more stable element. We can see that we have a new element and a helium atom from the reaction. With a change in mass number of 4, 2 neutrons and 2 protons, the 2 protons would cause a decrease of 2 in the atomic number. Likewise, the radioactive element of most concern in the Fukushima disaster, cesium-137, also has a half-life and a decay reaction. Cesium-137 has a half-life of about 30.17 years. About 95% of it decays to barium-137. As you can see, nuclear power, though attractive in its lower carbon emission, has the ever-present danger of massive amounts of radioactive product release, if not contained, that persist in the environment for many years. Discovering replacement means of electricity generation and managing nuclear power reactions and waste in the meantime will be imperative tasks for society for some time to come.